Let's look at an example. So suppose you're a sociologist and you're looking at the social network of friends on Facebook. You can think of a social network, person A might have 50 friends, person B might have 25 friends, but they might have some friends that overlap. So person A's friends is friends with person B's friends. Well, let's suppose you gather data on 40 students from London. Suppose it's a random sample. Then what you do is you measure the amount of gray matter density in the brain regions related to social perception and memory. Then you transform these measures into z-scores, or standardized scores. Then you also measure the number of friends on Facebook for each friend. Assuming this is a random sample, what is the correlation between gray matter density in the brain and the number of Facebook friends for all students in London? So we're assuming that this sample of 40 people, 40 students in London, we're assuming that it is a simple random sample from the population. So we have this variable GM density. It's a z-score of gray matter in the brain for social perception and associative memory. This is a real data set. And we also have the number of Facebook friends. So you can see that first person in the data set has this sort of negative z-score for gray matter density. So relatively low gray matter density compared to other people in the data set. But the Facebook friends, well, it's pretty low too. 23 friends. It doesn't seem particularly high. The 40th person in the data set, the 40th row, has quite a few friends on Facebook and a slightly positive gray matter density. The sample size is 40 people. So here's the sample correlation. So each of these data points, those are our 40 students, and we can see that we have a positive linear correlation. You can kind of see it in the scatter plot. The sample correlation is in fact 0.436. So we might say it's a modest or moderate positive linear relationship. It's a positive correlation. But here's the thing. This is a random sample from that population. Our goal is to say something about the correlation in the population. We know what the correlation is in the sample, but what is the correlation in the population? We just took a random sample. We don't know the correlation in the population. So to do that, we have to conduct a bit of statistical inference. The idea is as before, when we have a sample mean and we want to say something about, for example, a population mean. We want to use this sample correlation to say something about this population correlation. We can conduct a hypothesis test as well as a confidence interval. The main assumption for conducting this inferential process is that both variables are normally distributed in the population. So this is just the process. We take a random sample from a population, and we want to use that sample to say something about this population correlation, right? Just like before. There are several steps for hypothesis testing for the correlation coefficient. So we always have our preliminaries, right? And then we have these steps. First of all, you want to state the null and alternative hypotheses in terms of a null and alternative hypothesis, H subscript 0 or H subscript A. Then you select a significance level alpha like we've done before, typically 0.05. Then we compute the test statistic. Right? We're going to use statistical software to compute the test statistic, but it's a similar process as before. Then we assume the null is true and we make a decision by comparing the test statistic with a critical value or values, and then we compare the p-value with the significance level alpha, and then we state a conclusion. We can also conduct a confidence interval. So let's think about stating the hypotheses. So when we work with a correlation coefficient, the most common setup by far is a two-sided test with the null equal to 0. That should make sense, right? Because if the correlation in the population is 0, right, that's the null hypothesis, then that means there's no linear relationship in the population. Basically, we're saying we're going to assume that there's no linear relationship in the population. There's no correlation in the population. That's our null hypothesis. The alternative is simply that that population correlation is not 0. It's either positive or negative, but the idea is that it's just not 0. This is by far the most common way to set up a correlation coefficient, and it's the way we're going to focus on setting up an inference for a correlation coefficient in this course. Then for step 2, we choose a significance level alpha, typically 0.05, and of course we use alpha to compare with p-values, determine the critical values, and compute confidence intervals. For step 3, we compute the test statistic. Right? The idea is that this is a t-test. Right? The test statistic is usually called t, and it's given by this form. Again, we're going to use statistical software, but this is a t-test statistic. Right? The idea behind it is that you have the effective degrees of freedom, right, which is the sample size minus 2. Then you divide by 1 minus the square of the sample correlation. You take the square root of that and you multiply by the sample correlation. And that is our test statistic. Right? Again, we're going to use statistical software, but it's the same idea as before. Right? This test statistic, it's a t-test statistic. It lies on a t-distribution. The t-distribution, it has a shape governed by the effective degrees of freedom, which is n minus 2. And again, the test statistic, it just tells us how far our sample correlation is from the null hypothesis of a population correlation equal to 0. Then what we do is, once we use statistical software to compute that t-test statistic, we compare this test statistic with a critical value or values. The critical value is based on the significance level alpha. Since we're conducting a two-sided test where the alternative is that the population correlation is not equal to 0, we're going to use the following decision rule. If the absolute value of our test statistic is greater than or equal to t alpha divided by 2, then we're going to reject the null that the population correlation equals 0. Again, we're going to use statistical software to really obtain these critical values. You can also find a p-value and then compare that p-value or probability value with the significance level alpha. Again, recall the p-value is just the probability of obtaining a test statistic as or more extreme than the one we actually obtained under the assumption that the null is true. To put it in another way, under the assumption that the population correlation is 0. So for a two-sided test where the alternative is the population correlation is not equal to 0, the p-value is going to be 2 times the probability of obtaining a test statistic greater than or equal to the one we obtained in absolute value. This p-value has a very easy, nice interpretation because all you need is a p-value and you can compare that to a level of alpha. We're going to reject the null if the p-value is less than or equal to alpha. The mantra is that if the p is low, the null must go. That's the basic idea. Then with step 5, you can make a conclusion. We can make a decision to either reject or fail to reject the null, that the population correlation is 0, based on the previous step, based on using critical values or p-values. The idea is that if we reject the null that the correlation of the population is 0, then we can conclude there's no linear relationship between the two variables in the population. The key point here, though, is that remember what the correlation coefficient is telling us. It's measuring only a linear relationship. Right? It's still possible that there's a nonlinear relationship in the population, sort of a U shape, for example, or a squiggly line. The basic idea, though, is that with the correlation coefficient and this process of hypothesis testing, we can use a sample of data to say something about a population. We could also calculate a confidence interval with the correlation coefficient, just like we, for example, calculated a confidence interval with a sample mean. We can do the same thing with a correlation. Calculating a confidence interval, it's a little bit more complicated because the correlation is bounded between -1 and +1. We don't have a correlation that is +1.5 or -50. Right? So because of that bounding, the formula is a little bit more complicated, but we can still use statistical software to obtain these confidence intervals, and we can interpret them in roughly the same kind of way. Right? This is the beauty of statistics in the sense that once you learn the basics of statistics, it builds on itself. So confidence interval, the machinery is a little bit different, the calculations, but we still have a similar interpretation as before. So let's look and return to our Facebook study. So recall that we have this sample correlation between gray matter density and the number of friends you have on Facebook. And we want to say, are these related in the population? We know there's a positive linear relationship in the sample, but how about the population? Well, we obtain a p-value that is less than our criterion level of 0.05. So since the p-value is lower than 0.05, we can reject the null that the population correlation is in fact 0. You can see that this statistical software, it does give us the sample estimates for the correlation. which is 0.436, which is what we had obtained before. But it also gives us a t-test statistic, right? And then also gives us the degrees of freedom, which is the sample size minus 2, so we have 38. And it also tells us what the alternative hypothesis is. For this course, we're going to focus on, by far, the most common setup, which is that the true correlation is not equal to 0. That is by far the most typical setup. You can also see that we have a 95% confidence interval calculated for us. We interpret this in a very similar fashion to confidence intervals for sample means or sample proportions. We're 95% confident that the true correlation of the population is between 0.144 and 0.658. To put it another way, we're pretty sure that there's a correlation in the population. This sample correlation that we observed, it's pretty unlikely to exist due to random sampling variability, due to the fact that we have a random sample and we gather this data set through this process of random sampling. It's very unlikely that we would obtain this correlation under the assumption that the population correlation is 0. So with that, we've covered the basics of hypothesis testing. So when you have a sample of data, you calculate the correlation, you can make inferences. You can say something about the correlation in a population.